Hello everybody, Dr. White here with a treatment of random variables of the continuous type. It's our real introduction to the subject. We've dealt with continuous type random variables intuitively before, and actually in the context of what we are now going to call uniform distributions. So I'm just going to start you off developing the subject with that particular type of random variable. So uniform distributions. Let's let A and B be fixed real numbers, and A needs to be less than B, okay? And let's let X be a real number in the interval AB. That's our random variable. What we're imagining is that you're picking from the interval totally at random, so every real number in that closed interval is supposed to be, quote unquote, equally likely to be the number selected. And so if I can succeed in defining this type of random variable in a nice formal way, I'll say that X has the uniform distribution with parameters A and B, A the lower endpoint and B the upper endpoint. So let's review the intuition we have about how these random variables ought to work. If you imagine the real number line with A and B on it, and you imagine some, say, open interval, U to V, what's the chance that X lands in that interval? What's the chance that you pick something in that interval? Well, it makes sense that it would be the length of the interval from U to V divided by the length of the entire interval you're picking from. I think that should be more like a closed bracket, I would say. The length of the interval from U to V is the upper endpoint minus the lower, and it's the same for closed interval as well, upper endpoint minus the lower. So that ratio. And that's something you've used before in some examples and exercises. Now, I just want to point out something that your intuition plus the laws of probability is going to commit you to, something that you might not have just intuitively figured. What about the chance that X is in the half-open interval from U to V? Okay, so bigger than or equal to U, still less than B. So graphically, we're looking for that chance. And if you just use your intuition, you're still doing the length of the interval from U to V, which is still V minus U, over the B minus A. It's the same probability as landing in the open interval, even though you've added on that extra possibility that X could be exactly U. Now think about this. The chance of landing in the half-open interval is gonna, well, you can express the event of landing in the half-open interval as a disjoint union of those two events. X is exactly U, X is in the open interval. And because it's a disjoint union, you can sum the probabilities. So I don't know why so now we're down to here. And, we just figured intuitively that the chance of landing in the closed interval is the same as the chance of landing in the open interval. So in this next line, I've just replaced the one with the other. And now I've got an equation that says chance that X is in the half open is probability that X is U plus same chance that X is in the half open. Subtract chance that X is in the half open from both sides of that equation. And you're left with probability X equal U has to be 0. So you're forced to conclude, if you want to preserve your intuitions how this random variable works, you are forced to conclude that even though it's possible for X to be U, the chance for X to be U is 0. So for these types of random variables, probability 0 does not mean the same thing as impossible to occur. That's something to keep in mind. Well, anyway, how can we make our intuitions about this type of random variable mathematically precise? What we need to do is to propose a cumulative distribution function that satisfies those intuitions. So I'm going to propose this one here. So this is what I want to be the probability that X is less than or equal to little x. This capital F of X here is a piecewise defined function that's going to be 0 if X is less than A, It's going to be that thing if x is anything from a to b, bigger than or equal to a, but less than b. But as soon as you get to b or higher, it's going to be a 1, okay? So here's its graph. And I can make sense for you of parts of it. Well, first of all, let me just convince you that this is in the running at all. I mean, could this be a cumulative distribution function for any random variable at all? Here, I'm just going to take off my shoes while I talk. There are 4 things that a function has to do to be a cumulative distribution function for some random variable. It has to have a limit as x goes to minus infinity of 0. Well, that is totally happening here. It has to have a limit as x goes to plus infinity of 1, and that is totally happening here. Not only just a limit, you're actually just like equal to it after a while. It's doing those 2 things. It has to also be continuous from the right, and this function is just straight up continuous. Great. And finally, it has to be a monotone non-decreasing, so it can't ever fall as you read it from left to right, and this one never falls. So it is a valid cumulative distribution function. Furthermore, it's given us what we think ought to be the case for uniform random variables when a is less than 0. So when x is less than, when x is less than a. Like, imagine that x is this number here where I'm just like waving my cursor, okay? What's the probability that x is, capital X is less than or equal to that little x? Well, it has to be 0 because capital X has to be between a and b. And this is what f is saying. Great. Similarly, what if little x is like this number here, something bigger than or equal to b? What's the chance that capital X is less than or equal to little x? Well, again, because capital X has to fall between a and b, then it has to be less than or equal to little x. The chance has to be 1, and that's what the graph of capital F is saying. So those parts of the graph are matching our intuitions. Now, there's this part where it's rising, and maybe that's not so clear. But initial indications are good because when you look at the formula for that rising slope line, you see that the top of it could be thought of as the length of an interval from a to x, like say if x were here where my cursor is. So the length from a to x is the x minus a. And then we're dividing by the b minus a, the length of the total interval. That's what our intuition says would be the probability of landing in the interval from a to x. So it's matching that intuition. It's also like matching our intuition for intervals that lie totally inside of the AB interval. For example, imagine that u is less than v, and that u and v are like both in between a and b. How about if we look at like the probability of being in the half open interval from u all the way up to and including v? I will argue that it's equal to this probability right here. And the way to see that is to take this equation and just add probability x less than or equal to u onto both sides. Okay, so do that on a sheet of paper and then come back. Okay, you're back. On the left-hand side, you got the sum of probabilities of disjoint events. So that's the probability of their union. But the union of those 2 events is exactly this event. So really, this equation just follows from our basic laws of probability plus the little algebra thing of subtracting from both sides. Now, this, by definition, this is what we propose that capital F of V ought to be, and this is what we propose capital F of U ought to be. And let's see, here's what capital F of V is defined as. Here's what capital F of U is defined as. And you know, they do, that simplifies out to what our intuition does demand. So I think I've like pretty roundingly convinced you right now that we ought to go ahead and mathematically just define the uniform distribution from A to B as being a distribution whose cumulative density function is this capital F. So I'm just going to take that as done. Well, discrete random variables had CDFs and they had Pmfs. Do uniform distributions have Pmfs? And no way. Because there is no smallest possible difference between their values. Think about a uniform. It could be 0.56, like say if you're just randomly picking numbers between 0 and 1, real numbers between 0 and 1. You could pick 0.56, but you could pick 0.561 or 0.5601 or 0.56001. There's no smallest possible difference between your values. This is just totally not a discrete random variable. And like, how would you even make a PMF? I mean, you'd have to make like a list, right, of all the possible values on one side and their probabilities on the other side. And this list here would be like a list of all the real numbers between A and B. It would be an uncountably infinite list. And furthermore, on the right would be a bunch of zeros, as we have already figured out, you know, because the chance to be exactly anything is 0. So such a table, if you could even make it, would be totally useless. No PMFs. But there's something like a PMF, and I want to edge you towards thinking about it. Think back to the very first discrete random variable we looked at. Number of heads and 3 tosses of a fair coin. So here was this probability histogram with rectangles, each of which had a base of 1 and a height equal to the chance of getting that number of heads. And here was the cumulative density function. And, you know, think back to how the cumulative density function behaved as you move from left to right along, you know, like the x-axis here. It stayed constant for a while, but as soon as you got to one of the possible values of the random variable, it jumped up. And it jumped up by an amount equal to like this little area here, 1/8 times 1. And then it stayed constant again until you got to another possible value of your random variable, and then it jumped up by 3/8 this amount here, this area of the rectangle over 1. And it just kept going like that until it had jumped all the way up to 1, and then it stayed. So it's basically the values of the CDF function. They were essentially sums of areas underneath the probability histogram. It's just that you weren't allowed to add on any more area until you got to another possible value, okay? Now, discrete random variables, the possible values are separated. And so you're gonna have, for their CDFs, you're gonna have these little intervals where the CDF stays the same, right? But for these continuous type random variables, like the uniforms, the possible values aren't separated. You know, they just keep coming at you, real number after real number. And so it's like the CDF is going to be able to get bigger and bigger and bigger all the time, you know, with maybe none of these intervals where it stays flat. And it's going to be as if capital F of X, the CDF, is like a sum of areas underneath some function that's like a PMF. And so I'll call that function little f for now, and I'll like identify it for you in a minute. But I'm gonna just like I'm just gonna like see if we could think about capital F of X being an area under the curve function, area under the curve little f, from -infinity up to little x. So if I do that, it's the little x that's the variable in my function. It's the upper endpoint of the definite integral that is the variable. So when I think about the little f function, I shouldn't think of it as a function of x. I should think of it as a function of some other dummy variable on the horizontal axis. So I think I'll just use u as my dummy variable. How about that? I could have used George as my dummy variable. And it would still be one of these area under the curve functions that you met back in Calc 1. But remember back in Calc 1, the fundamental theorem of calculus, there were two versions of it. There was one version that you used to find definite integrals, where you took the antiderivative and you evaluated it, upper endpoint minus lower endpoint. We do that a lot. And then there was the other version that actually was like really more important. And it was even used to prove, the version you use a lot. And it went like this. It said that when you have one of these area under the curve functions, where the upper endpoint is the variable, then the derivative of that function is the little curve that you're finding the area underneath, evaluated at x. So that would happen basically, whenever this, this function has a derivative. So like if you could set up a little f where that would happen, that would be great. I should have said wherever f is differentiable, not f where f prime is differentiable. Leave off the prime in your mind. Take it away. So I'm going to set you up a function little f that tries to do the job. Now, well, let's just go ahead and see how good a job this does. I'm going to say that little f is 0 if x is less than a. It's 1 over b minus a if x is between the two, including the a, including the b. And it's 0 again if x is bigger than b. And my rationale for this is to try to get it to be the derivative of capital F. So am I doing a good job? Let's think about how capital F is working. Capital F was supposed to be 0 for x is less than, or let's see, what was it? Less than a. Yeah, that's what it was. Well, the derivative of 0 with respect to x is 0. So I'm doing a good job there. And capital F was supposed to be like this between a and b. And the derivative of this with respect to x would be, okay, there's a constant 1 over b minus a multiplying a function x minus a. So we got a constant times the derivative of x minus a, but the derivative of x minus a is the derivative of x, which is 1, minus the derivative of a, which is 0. And so that seems to be working out. Now I'm claiming that for x less than or equal to b, which is a little bit of a fudge because see, f was only that way when x is less than b. It's a little bit of fudge. Give me that. Let me keep going. And for x bigger than b, then capital F said that x was a 1, but the derivative of 1 is 0. So I seem to be in good grounds putting that here. Okay, so a modulo of some little fudges. I have something that seems to be like almost everywhere the derivative of capital F. In fact, it actually does match up totally. If you just put the two functions together, you really see there's a total match. Whenever capital F has a derivative, it's equal to little f. See, capital F does not have a derivative here. That's a corner. You know that functions with graphs that have corners, they don't have tangent lines. They don't have a unique tangent line, so they don't have a derivative. And there's another corner there. And that's precisely, well, okay, it's not really true. The capital F is defined here, and I've defined it to be like 1 over b minus a. Like if I were really, really going to make it match up, I would say that little f is not even defined at a and not even defined at b. to match that there's no derivative here and there's no derivative here. So I kind of didn't really come through on it. It's not like little f is equal to the derivative of capital F, like, and then is it undefined when f has no derivative? There's a little bit, I'm making this one defined at all real values. And that's what we're going to do with these little f's. So we're going to be like little fudgy at the endpoints. But the key thing is how it works with areas underneath. That's really the only important thing. Check it out. Look at the probability that our random variable is less than or equal to little x. So, like, is it equal to the area under the little f curve all the way up to a little x? Yeah, it is. So, like, if I just like put an x somewhere, like here, the area from a to this x is this base times this height. And so the base is an x minus a, and the height is 1 over b minus a. It's the x minus a over the b minus a, you know? And what's, like, if x is less than an a, what's the area under the curve less than it? 0, because the curve's at 0 height. And so it's giving the answers for the probability. It's giving the capital F answers everywhere that it needs to. It's even doing it for, like, you know, the intervals UV that are inside. Then you would just be doing the area underneath the curve from U to V. Like if U were here and V were here, okay? Then you would get a V minus U base times a 1 over B minus A height, which is, again, intuitively the area. Notice here where I've got my U and V being upper and lower, I couldn't use a U as a dummy variable anymore to express the curve, so I switched to a non-clashing dummy variable. I switched to an x. Anyway, what's happening is for this little f curve, it's giving you the chances for x. Areas underneath the little f curve give you chances for x. Just like with the probability mass function, areas give you chances. Like those two areas from 1 to 2 gave you the chances of getting 1 or 2 heads. It's working the same way with this little f function here. So this little f function is not the only one that I could have used. I could have used one where, like, I defined little f at a to be a 0 instead of the 1. And I could have made a similar choice here at this other jump. So the little f functions are not, like, unique. There's several different ways to set them up depending on, like, how many jumps you have. But at least they're there. And no matter which one you pick to use, they do the same area underneath work to give you probabilities. So because the little f works like the probability mass function, we're going to call them probability density function. Okay, the little f's. Oh, and look at this. They're even delivering that thing that had to follow from our intuitions, that the probability of being exactly a particular value in a continuous random variable is 0. I mean, check it out. Like, say x is right here. What's the probability x is x? Well, it would be the probability that capital X is bigger than or equal to little x and less than or equal to little x, you know? And so that would be the quote-unquote area of this little rectangle here, which has base 0, so its height being 1 over b minus a does not keep its area from being 0. And so the probability is 0, like had to be the case. So the uniform distributions from a parameter A to a parameter B are the first family of random variables that we're meeting that are of the continuous type. And the way you should, the way the book suggests you should define continuous type random variables in your mind is that they take their possible values in intervals of real numbers, like the interval from A to B. And the derivative for the cumulative distribution function may not exist at all x's. They did not exist at A and at B for this family. So there may not be just one PDF, but they'll go ahead and define a standard PDF for you, and they're all going to give you the same area computations no matter what choice was made. Like this one here that decided that f of a should be 1 over b minus a versus this one that decided that f of a should be 0. They're going to give you the same area computations. They're going to relate to the same capital F. Anywho, keep this picture in mind for probability density functions. Now just imagine some curve that's your probability density function. Areas under the curve give you chances. So if you want to know the chance that capital X is between U and V, just run to your calculus and compute the area under that PDF from U to V. It's a definite integral you've got to do. The following idea is wrong because it's like overly intuitive calculus, but it's really useful wrong. Think about a particular value x. And so like here's the height of the density curve, f of x above it. And let's kind of zoom in on that little line segment. But instead of thinking of it as just a line segment, think of it as a very skinny rectangle whose left-hand endpoint is x on the base and whose right-hand endpoint is x plus dx, where dx is like this infinitely small positive number that you threw on, okay? Skinny, skinny little rectangle. And so the area of that skinny rectangle would be the height times the base, which would be dx, okay? And so you can think of that quote-unquote area as like the probability that the random variable lands super close to little x. And you can think of some definite integral like this as adding up those little skinny rectangle areas. And so it's adding up the probabilities of a bunch of mutually exclusive events. Chance you come close to this little guy, chance you come close to this little guy, and so on. So formally, definite integrals are limits of the sums of areas of real rectangles. But if you think about them this way as the sums of infinitely skinny rectangles, it can be very helpful. It's really it's adding up probabilities. I think I've gone far enough for now in this screencast. So we'll talk about expected value and other types of special mathematical expectations for continuous distributions in a future screencast. See you soon.